Are you ready? Please go ahead.
Yep, I'm ready. Thank you. Hello, everybody. I'm Songbo, a PhD student with Dr. Yihai Fang and Dr. Robert Moehler from Monash University, Australia. Let me introduce our work estimating hazard exposure in tall crane lift operations using beam and path planning algorithm. Yeah, in Australia, there is more than 70% of work-related fatalities happens in construction industry. On average, there are 31 people die and 12,000 plus people seriously injured per year. Crane-related accidents is one of the major contributors to the poor safety record. In particular, for tall cranes, it's more difficult to recognize and mitigate. Many hazards cannot be identified in time, and it's often very costly and even impossible to mitigate on the spot, such as struck by falling load. Thus, early prevention is critical, also known as prevention through design, PTD. This theory aims at design out hazards or eliminate them in design and planning phase. There are 4 common trajectories to materialize such a theory, including prefabrication, avoiding hazardous material, incorporating engineering calculations, and considering spatial requirements. So our aim is to propose such a PTD system for tall crane planning, adopting the last 2 methods, incorporating operational considerations and communicate spatial temporal information of the hazard before construction starts. To communicate hazard is not a new thing. A lot of research works have proposed some quantitative models to estimate tall crane related hazards. As the diagram shows, the risk zone that are exposed to crane collapse and the load dropping can be formulated with the crane specifications, such as mast height, boom length, and locations, or can be formulated based on the location of a tall crane only, assuming the hazard decays with distance. However, the spatial granularity is insufficient, which didn't consider the trajectory of lifted loads and ignored the transition of hazards. Also, there is a research work on the right side, monitors the crane hooks and estimates the hazards accordingly, which is a very good spatial granularity, but it's as is in nature, which is not proactive enough. Meanwhile, common limitations shared by them, which is only focusing on the gravity-related hazards using 2D analysis. Some other types of hazards remain uncontrolled. So a big question follows, that is, what hazards are there in addition to gravity-related ones? To answer this question, we use an energy-based hazard identification method. The underlying theory of this method is that every accident have an energy source, which can be identified before work starts. There are 10 energy sources on construction site which comprehensively categorize and enumerate all hazards in the construction scenario, as the left diagram shows. So we apply this method to tall cranes and use it to organize accidents data, such as fatalities and near misses in previous empirical studies around the world. As a result, we found 15 types of crane-related hazards with 4 energy sources: electrical, motion, gravity, and chemical. Although some of them are not happening because of the crane operations, such as direct human contact with power lines or explosion, the rest of them can be controlled by meticulously planning crane operations. By recognizing the gaps, we revised the aim here. So systematic means control all identifiable hazards aforementioned, and 2 methods are used for different types of hazards. One is by incorporating operational considerations such as collision detections and crane load capacity check. We control some collisions and control overloading. Such consideration is incorporated in the path planning module, module 2 here. With our novel path planning algorithm reported in 2021. By communicating spatial temporal information of the hazard at the second method, we estimate the site's hazard exposure to tall crane related hazards as in module 3 and 4 here. In particular, 5 types of hazards are managed with electricity, motion, and gravity energy sources. The hazard exposure, HE, is calculated and visualized in beam models. The holistic research framework presents here, which first extracts the site topography, existing structure and the geometry and the weight of the lifted loads, then exports to path planning module, which generates a collision-free path compliant with the load capacity limit. The results provide detailed trajectory information for hazard exposure estimation and visualization. So as a result, the beam model is enriched with hazard information for communication and even further analysis, such as evaluating different set layout of crane repositioning, using clash detections, and etc. Today, we will first brief about the path planning module, then goes to the mathematical models used to calculate the hazard exposure, the HE, and the visualization module on beam. So the core of a path planning module is based on our work, practicality and a safety-oriented approach for path planning in crane lifts. This work first identifies all the unique practicality considerations for crane path planning, such as shortened path length, avoid unnecessary movements and direction changes, limited coordination of multiple operations, and maximize visibility. And we found out that although frequently mentioned, none of the previous work have systematically incorporated them all. So we modified a RT star algorithm to get a practical guidance to crane operators. For example, in the diagram down here, we have an observer at the right point. And after the modification, the algorithm avoided the path in the blind side as for the practicality consideration for visibility. Details can be found in our paper, but what is important for the hazard exposure is that the practical path can be actually executed by the operator, which provide a reliable estimation of the trajectory and these hazards. So with a reliable estimation of trajectories, we describe the hazard as accumulated risk of multiple tall crane-related hazards, including electrical, motion, load dropping, boom failure, and crane tip over. The 5 types on the one 3D location, say X0, Y0, Z0. We describe likelihood of occurrence with W and P, which is how likely an accident happen in the hazardous zone and how the risk distributes within the hazardous zone using 0 to 1 scales. Then we use E to understand the amount of damaging energy. For the electrical hazard, for example, it happens when the load or cable contacts with the power lines and workers get close to the crane mast. Thus, W1 represents the likelihood of power line and load contacts, which is shown in the right bottom diagram, determined by distance between power line and the loads. Meanwhile, the hazardous zone locates around the crane foundation. In the high-risk zones, right zones, the energy does not decay, while in the medium zones, the energy decays linearly. EE is a user-defined constant to show the electricity power that gets through the crane. For collisions with a moving load, W2 equals to 1, which means the accidents are bound to happen, definitely going to happen if a worker enters a hazardous zone. And PM is the reduction factor of the kinematic energy, EM, which decreases in medium risk zones linearly as shown to show the uncontrolled load sway. For load dropping, W3 is a user-defined constant representing the likelihood of crane cable and lifting gear failures. The load's potential energy, EG, is reduced by PG linearly as well. Boom failure and crane tip over have a W as a fraction of W3, which is determined by the construction practitioners. Meanwhile, P value for them are set as 1, so the HE uniformly distributes in the hazardous zones. E for these two hazards are the potential hazards calculated by the crane weight and geometry. Here is a work in progress of visualizing such HE, the hazard exposure. This building is a real-world project in Melbourne, Australia, and the diagram shows we have planned the path using the module 2, path planning module. And for hazard visualization, we first extract the existing structure from BIM model, and then find one open spaces in 3D, such as open spaces above the building, besides the building, or above on the ground. This is actually the accessible hazardous zones for workers and machinery. Then we voxelize the space with the cuboids, which is known as eco-sized voxelization. Here are the third picture is the voxelized hazardous spaces in Dynamo and Autodesk Revit API 2. Then we are going to use the centroid of these voxels to calculate the HE and store the HE voxel attributes and show them in the BIM model with the color schemes. In this way, human planners can easily understand the hazards for one lift operation or multiple lift operations, such as a cycle of installation. And this information could help the planners to make better decisions.